So this is force on a wire. We're going to look at the forces that magnetic fields exert on wires. I think I can get this out of the way. You guys don't have to. Okay, I think I've got it set up the right way. So here's a formula that predicts the magnitude of the force. That force is I times L times B times the sine of the angle. Okay? And so F is the force on a wire. So let's suppose we've got a magnetic field that is, and I'll draw the magnetic field in blue because it makes me happy to draw things in blue. Let's suppose I've got a magnetic field that is like this. Yeah? Okay. So this is our B field. And then, of course, let's just try the case where we don't get any force at all. We've got a wire flowing parallel to the field. Yes? Well, the angle between this wire and that magnetic field is 0, or it's 180. It depends on which way the current's flowing. If it's flowing that way, it's 0. This way, it's 180. Sine of either one, though, is, careful, it's not 1. It's 0, yeah. Sine of 0 is 0, okay? So if the magnetic field and the current are parallel to each other, there's no force, okay? It's only when they are perpendicular to each other. Now, nobody knows why this is. We've got rules that explain it, and it always is this way, but there it is, right? But now if we've got it, if it's at least some part, right? So we'll have a current flowing this way, say, right? Okay? So there's our current. The black one is our current, okay? That angle that we would use then is this angle here, the tail-to-tail angle, okay? Tail-to-tail angle like that. B is just our magnetic field, and our magnetic field is in Teslas of B. And a Tesla is huge. Like a 1 Tesla magnet is just a very, very strong magnet. And Mr. Bossy, I wish he was here, but you know, I think I don't know how many Teslas we've gotten to, but that's where he worked. But a 1 Tesla field is really, really strong. We probably generate that with our hard drive magnets. The magnets that are holding my oven shut, okay? The latch on my oven broke, so I took old hard drive magnets, screwed them to the door, and now boy, it shuts really good now. It's like, kaboom, right? It's like, you know, and then they've lasted. They've taken a beating and kept on, you know, going. The magnets don't like to be slammed into things because it rearranges their little domains. Our magnets they're going strong. All the things you're not supposed to do, magnet heat and percussion, right? L is the length. Okay, so if we've got this guy here, if the magnetic field is restricted to this little area right here where I've drawn it, then L is, of course, this length. Okay, and then I is the current in amps. Amps of current. And L is just meters of length. Like it says on there. There we have it. Okay. Now, the question is, which is the direction of the force, right? So I think I've got it set up over here. I've got this thing set up in this case. We've got the North Pole magnet on the top, South Pole on the bottom. We've got the current is flowing to the left like that. I think it's the way it is, yes? Okay. And the force is in a very strange direction. What do you think it's going to do? I'm about to turn this on. 4 amps or 120 amps of current is going to flow that way. What's it going to do? Do we have predictions? Explode, burst into flame are the predictions I'm hearing. No, it's much more boring than that. Nina's like, she's like figuring this out. Yeah, okay. If you look at it, I've got it set up so it can swing this way or this way. So it seems like in or out of the magnetic thing is going to, isn't that weird? Okay, so notice that which way is the magnetic field?
Down.
Magnetic field is down, the current is that way. And so if it moves in or out, that means that the force is perpendicular to both of them, which is a weird thing. Okay, let's watch. We have a prediction. How many say it's going to go in? How many say it's going to go out? Out?
Towards us.
Toward you. Here we go. Are we ready? And toward you is correct. There we go. A little applause for that demonstration. Yes. All righty. Here we have it, right? Now, here's how you predict it, okay? And I used this. There's lots of ways to do this, okay? But this is our third right-hand rule. And the third one is I L cross B. And this is what we're doing actually. It's called something called a vector cross product. IB does not write it that way, but what it really the way this law is written is that it's the force is I L cross B. Okay? Now A cross B in math is AB sine theta in the right-hand direction. And I think mathematicians have some clever way to write that, okay? But it's AB sine theta in the right-hand direction, and so that's what it is, right? We're not making up something new here. It's something that mathematicians have been doing for a long time, okay? So IL cross B, what you do is you do your index finger as the current, okay? Yes? Your middle finger as the magnetic field, your thumb is the force. Yeah? So if you look at your fingers, it spells biff. Yes? If you hold your hand that way, it spells biff, doesn't it? It is cheating to write on your hand right before a test or skill set. I'm just kidding, I don't know. If it helps you do it, you know. I once gave this test at the private school that had all these magnetic fields, and the kids had to do this. And I taught them there's another way you can do it, where you put your arm in the direction of the current, and you bend, I think, like this. You bend your hand to the direction of the magnetic field in your thumb, right? And so the kids are sitting there on the test going, you know, and right like this. And there was another teacher proctoring the test, and she pulls me aside. She goes, "What are they doing?" She should have known. I mean, she's a mathematician, right? And she said, "Are they cheating?" Right? They had like some complex sign language that the physicist said. Like this, right? Okay, this is much better. I learned this from a kid who came from Hong Kong, and this is Eugene Lau. I remember his name anyway. This is much easier to do. But it's more fun to do, you know, hands this way, arm that way, or something like that. But there we have it. So let's predict this direction. Okay, let's just check this rule out, right? This thing should predict that the force is toward you. Yes. So fingers this way. Yes. Now the magnetic field is the next one. So extend your middle finger. Yes. Which way is the magnetic field going? Well, it goes from north to south. North is on the top, south is on the bottom. So our middle finger should now point down. Which way is our thumb pointing? Out. Why does it exert a force that way? I don't know. Nobody knows, but it always acts this way. It's a fundamental law of physics, right? So if you want to ask some really trivial question of your maker, I think you get to ask your maker a question, don't you? When it's all over. It's like a final call to your lawyer or something like that, right? Magnets, how do they work? Right? Okay. But anyway, there it is, right? You know. Now, I know that this seems biased against left-handers, that we're always using our right hand to do this, but understand that it's not a bias, it's a gift. Right-handers cannot, left-handers can be like doing the right-hand rule with their right hand, writing the answer with their left hand. Left-handers are always like, yeah? So it's a, you know, a small disadvantage. There we go. Okay, let's try some of these guys. Direction, middle finger. Oh, we've already got this. Review the demo. Okay, I've done this. I am on track. This thing is telling me what to do. Not that I'm so spacey that I can't do this, right? But there it is, right? So index finger is the direction of the current, middle finger